Hi, this is Raphael Mudge, and in this video, I'm going to demonstrate how to implement Syscalls in the Cobalt Strike artifact kit, but we're going to take advantage of the work that Outflank did with direct Syscalls and beacon object files to do it. So for the sake of the blog post that this video is embedded into, I'm actually mixing and matching techniques presented by two members of our community. So what's great about this blog post here is it takes us through the steps to update Cobalt Strike's artifact kit to use direct syscalls, which can be pretty handy for hiding some of the steps we're taking to inject into our own process. And this post starts out with an introduction to the artifact kit. It talks about porting the artifact kit over to Visual Studio, which, by the way, is something I recommend that you do, but I like to use the minimal new for Windows compiler because it is available on Kali Linux. Like, I just like working from Linux, so we're not going to do the Visual Studio step here. And that's why we're going to take advantage of Outflank's work so we can work from the minimal new for Windows compiler. But this post does talk a little bit about SysWhispers, how things work, and then it talks about how to port some of the functions in Cobalt Strike's artifact kit to their NT equivalents, which are exposed via SysWhispers. So pretty handy stuff. Anyways, let's go ahead and go through this. So we're going to kind of go this in 3 parts. We're going to get everything kind of compiling with SysWhispers. So we're going to play around with Outflank's code called inline whispers, get everything kind of compiling with it. We're going to actually update our code in line with the recommendations here in this blog post, and then we'll test it out on Windows 10. So that's the process we're going to go through right now. All right, let's go over to the artifact kit. And I just extracted this, but the first thing I'm going to do is initialize a Git repository, because beautiful thing about Git is we can go back and forth. We can see what changes we made. So I find that, even though like I'm just doing a one-off customization, I find working from Git to be very nice. So I recommend you do that when you're playing around with the artifact kit. As for compiling the artifact kit, let's go there. We can use build.sh to do that. So build.sh, press enter, and this will compile the artifact kit and the different built-in bypass examples. And that's what you're seeing happen right now is everything is being rebuilt, which will take a minute. A long minute? No, it's not really that long. But it's good. It's good to see the process. I certainly recommend you go through the other video I have on Artifact Kit and the documentation. That will help you become an expert on this process and how the Artifact Kit is laid out. But let's just go ahead and let this thing finish. And there we go. We've compiled the artifact kit. Great. Let's go to dist template. And what I'm going to do is just run strings on artifact64.exe. And we're just going to grep for virtual. And I just want you to see that we can see part of the import table. So you've got virtual alloc, virtual protect, virtual query. So those are the functions we're using to allocate memory. And we're going to change those when we bring in our direct syscalls. We're going to kind of get rid of virtual alloc, and we're not going to use virtual protect. We're going to use a direct syscall instead. By the way, something else you can do, come over to Cobalt Strike. If you use p clone dump, and let's go to artifact kit, this template. P clone dump is a way to see the output of Cobalt Strike's built-in PE parser. And here we can more quickly see the import address table, like what's being imported. So yeah, if you don't want to run strings and want to take a look at things this way, you can do that. Cool. So at least now we have a way to verify what is and what is not imported. So that's the whole point of that particular exercise. Now let's go ahead and start out with a fresh build of inline whispers. So I'm going to get rid of the one I pulled down earlier. And we're going to come over here to Outflank's blog post. And what's great about Outflank's blog post is they talk about how to do direct syscalls from the minimal new for Windows compiler, which is pretty handy. So we're going to take a look at their process, and that's going to save us the trouble of having to port our artifact kit over to Visual Studio, which again is a valuable exercise. I just don't want to do it right now. All right, so let's go ahead and download a program that Outflank released called Inline Whispers. And we're just going to grab this over here. Come over here, git clone, paste. Let's go to the Inline Whispers folder. And let me explain how this works. So Inline Whispers is a Python script, and what it will do is you tell it the functions you want in a functions.txt file, and when you run Python 3, very important, Python 3, what it's going to do is read in functions.txt and syscalls.asm, which was generated by syswhispers1, and it's going to output a file syscalls.-asm.h that incorporates the function specified in your functions.txt. That's it. Okay? Easy enough. So what we're going to do is we're going to tailor this to what we want because let's go over to our artifact kit. Let's go to source common. And let's grep for where we do memory things. You can see we do virtual protect, virtual alloc, and virtual alloc x, virtual protect x, and patch.c, and injector.c. Injector.c, by the way, is the part of the artifact kit for artifacts that migrate to a new process. So Cobalt Strike spawns a process, or excuse me, the artifact spawns a process and injects our position independent code into it. This file is a great candidate for stuff to port over to direct syscalls because userland instrumentation of a process using hooks is used especially to detect process injections. So direct syscalls is a great tool to make this more stealthy against some types of endpoint security products. And I highly recommend, if you're looking at this technique, that this is something you consider. But the only artifact in Cobalt Strike that migrates by default is the service executable. The service executable is the only one. And it does the migration because that allows Cobalt Strike to clean it up right away, to clean up that executable. Patch.c is the other file. And here you can see we've got at the top here, if def migrate, we call a spawn function and we migrate to Rundle32 by default. Something you want to change because you don't want to migrate to Rundle32. That much is usually for certain. But otherwise, back to boring, we have spawn and run here, and spawn just calls virtual alloc. It does some decoding of our embedded position independent code with a 4-byte key. Takes care of smart inject if that's set up, which I highly recommend taking advantage of smart inject. And then it calls virtual protect to make this code read executable, and then it calls create thread. And so what we're going to do is we're going to update our executable to call virtual alloc, virtual protect, create thread with their NT equivalents. That's what we're going to do. So we're going to follow the ideas here in implementing syscalls in the Cobalt Strike artifact kit. So let's go down to where they talk about porting Cobalt Strike's virtual alloc, virtual protect, and create thread to the internal NT versions. And so we've got a few function prototypes that we're going to bring over, and we're going to end up eventually with a function to allocate memory, change its protections, and then create a new thread. Easy enough. So let's go ahead and get started on that process overall. First things first, let's specify these functions in our functions.txt with inline whispers. Let's get rid of all this other stuff because we don't care about it. Paste. Let's come over here, nt create thread x, copy, paste, and there was one other prototype. It was the alloc, virtual alloc, or nt allocate virtual memory. I almost never use NT functions if I can get away with it. I have a kind of weird offense philosophy. I actually try to do things like the normal documented way as much as possible and deviate from that only when I want to, only when I have to, or only with a user-specified option. And I'm a big believer that one way to achieve stability, evasion, backwards and forward compatibility is actually just to do things the documented way and bring in the cute tips and tricks only as needed. So that's just a philosophy thing that I have. Anyways, we've got our functions.txt. Let's do Python 3, inline whispers, and our syscalls ASM should be a lot smaller now. It is 12 kilobytes. And you can see now that we've got NT protect virtual memory, NT create thread x, and NT allocate virtual memory. Very handy, very, very handy. Okay, the next thing to do is actually get this thing compiling inside of our artifact kit, like just actually getting this inline assembly to work. And we're going to take advantage of some of the advice given to us by Outflanks. So let's go to artifact source common. So we're just going to copy syscalls.asm. And we need to actually copy syscalls.h as well. Easy enough. Syscalls.h, syscalls.asm. Let's come over here. And what we're going to do is open up patch.c. We're not going to do anything if we're migrating. We're leaving that alone for this demo. But what we are going to do is include syscalls-asm.h. And I think we need to include syscalls.h. Actually, syscalls-asm.h does that, so that's good. So I'm comfortable with this. One other thing I want to point out is that this is going to compile for both 32 and 64-bit, but syswhispers is 64-bit. So what we want to do is actually differentiate run and spawn here from a 32-bit versus 64-bit version. So what I want to do actually is this. Let's change, let's do pound elif. It's kind of an else if. And we're going to see if we're actually going to borrow some logic from startThread.c, which does if, def, else, and if. So what we're going to do is grab the M64 variable here, which is just our way of defining whether or not we're 64-bit versus 32-bit. So now I've got an else if for 64-bit, and that's where we're going to do the syscalls asm.h. Grab all this. We'll leave the 32-bit version alone, and there we go. So now we've got our run and spawn for 64 and our run and spawn 32. Perfect. Now let's go ahead and try to compile this. So let's come over here. Let's go to the artifact folder. We're going to open up build.sh. And what we're going to do is comment out everything except building the template artifact kit. And that's just save time. You could build all of them if you really want to, but we're just going to build the template for this demo. Let's do build.sh. And the 32-bit ones go first, and I don't expect any problems. Looks good. And right away, we're in the 64-bit ones, and you can see we are getting a fatal error because of windows.h with a capital W. The great joys of building Windows programs on Linux. So that's easy enough to fix. We just need to edit syscalls.h. So let's go ahead and do that. And we'll go from windows.h to windows.h. There we go. Let's try compiling again. The 32-bit stuff's going to build. And look at all this fanciness. We're getting a lot of errors with our inline assembly, right? Don't worry too much. If we come over here to Outflank's blog post, they give us some guidance on how to do inline assembly in a minimal new for Windows compiled program. And what we need to do is change the dialect of MASM. So we need to make it use the Intel syntax. And they provide the recipe to do that in here. It's pretty easy. It's right here. It's dash MASM equals Intel. So let's copy that. And let's go ahead and open up build.sh again. Go to the bottom. Or we can go look at any of these. And what I want you to see is we've got the compiler command, and then we've got a option $options, and that propagates options to all of our builds. So what we're going to do is update options, and we're just going to add that MASM equals Intel to the command line of everything. Easy enough, right? Build.sh. Let the 32-bit stuff build. And we're into the 64-bit stuff. And you can see that all of that is building without a problem now, right? Pretty cool. So there we go. We've accomplished step one of our big plan. And step one was just getting the inline assembly generated by Inline Whispers to compile. And we did. Very easy, right? So that's great. We're at a good spot. So let's go ahead and just do a quick git status. And we are going to update, we're going to add syscalls.h to our tree, syscalls-asm to our tree. Let's take a look at what we did to source common patch.c. And all we did here was separate 32 from 64-bit and make it so that we can start, and also including syscalls asm.h. So that's all we did. We just made it so we can start working on this porting over to NT functions. So let's go ahead and, and we've got, of course, our build.sh, right, where we updated that to use our MASM equals Intel and a little bit of a time-saving measure commenting out some stuff. So let's just go ahead and commit source common and build.sh, and we'll just be quick and just say use syswhispers. Initial. Whoops. Oh, perfect. I actually don't normally use the -M option, so I was kind of surprised by that output. I'm like, what's going on here? But everything looks okay to me. Just verify. Yeah, okay, we're good. All right, so great. We've compiled. We've taken advantage of Outflank's advice on using inline whispers, which is their tool to take advantage of sys whispers with a minimal new for Windows compiler. Perfect. And we've proven that we can kind of bring this into the artifact kit. Now let's go over to implementing syscalls, direct syscalls in the Cobalt Strike artifact kit. And what we need to follow now is converting to NT functions. So we're going to take our virtual alloc, virtual protect, create thread, and move these to the versions that have been redefined for us by the included headers for generated by inline whispers, so that we can make our direct syscalls. So what we're going to do first is just grab these function prototypes, bring them over to our artifact kit. And let's go to patch.c. We'll just do that over here. Paste, paste. Allocate virtual memory. We've got protect virtual memory. Oops, okay, that's okay. And we've got create thread X. Looking good. Allocate, protect, create thread X. Good, good, good. Like it. And the author of this blog post is giving us some tips on just some variables and things we'll need to define. And that's cool. I'm actually pretty comfortable, just for the sake of ease of use, using their variables and conventions. So we're going to create a variable hproc and a pointer for base address. So let's come over here to our spawn function, start changing things around a little bit. So we'll paste in our hproc, our base address. By the way, pointer now becomes base address over here. So we're just going to update this all. Base address. And the main reason I'm changing my variable names around is just to be consistent with the blog post, just to make it easier to benefit from their work, casting everything over to the right types. That's it. Otherwise, pointer is a perfectly fine variable. So let's do base address. All right, cool. Now, they're kind of giving us an idea of how to use NT allocate virtual memory. Actually, I think they give us just an example function, puts it all together. So we've got, first we allocate our virtual memory. And calclen, by the way, is the length of our payload. So they're kind of just showing us what that looks like. So let's just go ahead and copy that. And paste that in. So we've got hproc for the current process, base address. I'm not going to use calc length. I'm going to use length. So we'll just do a pointer to the address to length. And let's get rid of this stuff here. Let's do virtual protect. Virtual protect now. Now, one thing to point out is that ideally, we really should be checking NT status to see if the function failed or not. I mean, obviously, looking at the code for the artifact kit, you can see the artifact kit is guilty of not checking the statuses. So take that for what you will. But yeah, just take that for what you will. All right, so we got NT protect virtual memory. We're going to do, instead of calculin length, instead of old protect, we'll just do old. Whatever. This looks okay to me. Base address length, old. Now let's go ahead and change create thread to spawn a thread that runs our data. So let's see what they did over here. One thing that's pretty cool, I think, is that something I think is really cool is that I think it's really cool. You can do all this, but like I said, I think it's really cool also that we're inches away from making our process migration more stealthy, because you could see how this would port pretty easily over to the migrating code. You've got your allocate memory, change memory permissions in a remote process. You've got create thread in a remote process if you want to. So that's all really, really, really cool, really handy. So keep that in mind. Oops. Clicked over to our Windows 10 system. Don't need to do that yet. All right, let's come over here, and we're just going to paste that in. And we need a variable. I think it's just handle t handle. It's what the author of this post is doing. Yeah, handle t handle equals null. Let's go ahead and do that. Handle t handle equals null. Okay, allocate virtual memory, protect virtual memory, create thread X. We're passing our t handle. Our hproc, that's us. Our base address, that's us. This all looks good to me. Hi, this is Raphael Mudge, interrupting my own video because I want to point something out to you. In the video, I pasted in int create thread X and just kind of updated the arguments, including base address, and didn't even really think about what I was doing. I was just trying to make the code work. And that's okay. That's okay when working to get something working. But I made a mistake. That's an OPSEC mistake that is really important, because it's one of those just generic best practice things that we should always be paying attention to. And that is, when I used int create thread X here, I passed it base pointer, or excuse me, base address. And that is going to create a thread with a start address that is not backed by a module on disk. And that will make this artifact show up when somebody opts to use a heuristic like get injected thread. So it's absolutely fine to work to get the code working, but even as you're trying to get the code working, always think about the implications of what you're doing. And so what I want to point out is that this run code here, this little shell code runner that just takes a parameter, is really important, because its purpose is to run its arguments. So ideally, we do the run function as our where our thread starts, and we pass the base address as an argument. That's what we really want to do. And let's verify that we just got the arguments right. Yeah, it's just start routine and then argument. So that's what we should have done in the video, but I wasn't thinking. I was just too excited copying and pasting from a blog post, too excited seeing all of it work. And so I just wanted to interrupt the video to bring in that detail, because I really do believe that offense is a detail sport. And we should always be thinking about not just getting the code to work, but what the code is doing and what the OPSEC implications are of that. All right, with that said, let's go back to the video. Our hproc, that's us. Our base address, that's us. This all looks good to me. Get rid of that. And there we go. We now have our spawn function with our int functions that map to our the stuff that we specified in our syscalls asm.h. So these are direct syscall versions of what are normally these NTDLL functions, and that should be a little bit stealthier against userland hooks that are looking at virtual alloc, virtual protect, and create thread. So that's what we're buying ourselves. Let's go ahead and compile it, just verify everything's good. So build 32-bit stuff first. 64-bit. And of course, you're complaining, oh, because we don't use these stupid variables. Well, Control C. Yep. Let's just go ahead and get rid of the shame from our compiler. And let's change all that. Getting rid of those unused variables. Build.sh, 32-bit first again. And there we go. We're now building our 64-bit artifacts. And there we are. Now let's just go ahead and just do a little bit of kind of quick static analysis just to verify the import table looks like we expect. We'll do the quick version first. We'll go to dist template, strings, artifact, 64.exe. You can see we call virtual protect virtual query, but not virtual alloc. And we're not calling create thread or anything else. Cool. Let's go ahead and take a look at, by the way, virtual protect and virtual query are very likely called by some of the C runtime linked into the default minimal new for Windows 64 binaries. That's why they get so big. So, you know, that's why not all of these functions disappeared, just some. But let's just go ahead and go over to our Cobalt Strike folder, p clone dump to use Cobalt Strike's p parser. We'll do artifact dist template, artifact 64.exe. Let's go look at the import table here. Just another way of the same thing. And you can see what we're pulling in from kernel 32, or excuse me, kernel 32 is up here. This is the stuff just built in. Import, or excuse me, that's MS Vision. It's the C runtime, excuse me. So nothing really too special here. But if we look at import 0, what you'll see, virtual protect, virtual query, but no virtual alloc, no create thread. So very cool. So we have moved over to our direct syscalls versions. And by the way, just to contrast that, let me show you the 32-bit version. Just show you that, yep, create thread shows up right there at the beginning. And you got virtual alloc, virtual protect, virtual query. Just so you can see without direct syscalls and with. All right, let's go ahead and make Cobalt Strike look at this. So we are now at part 3. Part 1 was just wrapping our arms around how to use inline whispers and generate a header file that we could include in our C programs, compiled with minimal new for Windows, and getting that compiling. Part 2 of this was following the advice in the implementing syscalls in Cobalt Strike's Artifact Kit blog post, which we did. And part 3 now is just trying it out on Windows 10, verifying that the binary runs and it works. That is the goal of this video. Let's come over here to Cobalt Strike, go Cobalt Strike Script Manager, press load. Actually, get rid of that. Press load. And what we're going to do is go to the artifact folder, dist template, because that's what we chose to compile, but we could have compiled all of them if we wanted. Artifact.cna. Let's go to text, web drive-by, scripted web delivery S, because I just want to do this quickly. Hit choose. Type is executable. We'll do 64-bit payload. We'll host this at test.exe. Hit launch. And now we've got a URL that we can go run on a target system to try this out. Let's come over here to Windows 10. And my goal with this demo is not to, go through the process of figuring out like what Windows Defender is doing. So I'm going to turn it off. My main goal is just to functionally verify that the binary works and runs beacon without in our version that uses direct syscalls. So we're just functionally verifying that we're working here. So real-time protection is off. Good. In my blog post, I'm going to give you pointers to some resources on which products hook what, or how to figure out what hooks what. And my advice would be take that information and combine that with your artifact kit. And if you see functions that are used by your artifact kit are hooked, update your artifact kit to use direct syscalls if you can get away with it. Why not? So no big deal. So let's just go ahead and hit run. So we're going to run test.exe. Of course, we get smart screen telling us no. We're going to go to more info, hit run anyway, and get that little waiting thing. That's okay with me. Let's come over to Cobalt Strike over on Kali Linux, and there we go. We have our test beacon on workstation 1 living in test1.exe. Apparently I used test.exe already. But that's it. That's what it looks like to add direct syscalls to Cobalt Strike's artifact kit. I'm going to close out with a couple things. First, to the author of this blog post, and I tried to find your name on your blog and your Twitter to credit you properly in the blog post, and I promise you I'd be doing it here. But nameless author or BS, no BS, whatever you want to call yourself, thank you for writing this blog post. Your blog post really did inspire this video. This video would not exist without your blog post. And so I found what you posted here illuminating and helpful, so thank you. And I want to also say thank you to my friends over at Outflank Security, who I am a big fan of. I want to thank you for your continued contributions to the community and this blog post, because not only did it help with the artifact kit, but holy cow, yes, I am incredibly impressed with the stuff I'm seeing folks do with beacon object files and direct syscalls and beacon object files. This is just really amazing back and forth, building off of each other collaboration, and it's just really cool. So I really appreciate everybody's doing. I appreciate the material you're putting out there, because I'm learning from you too. And so thank you. Thank you very much. And for those of you who this is your first go with direct syscalls, or even first go modifying the artifact kit, I hope you found this video helpful. And certainly my goal going through this step by step was just to kind of remove the ambiguity and show you, just so you can kind of just jump in and start doing it. And that's it. Once again, because I end all my videos this way, and I'm not about to change because I like ending my videos this way, but good luck and happy hacking.